3, 2, click.
Okay, there we go.
First of all, of course, thank you to our hosts, David and Jackie Nadich here in their beautiful home. Jackie and David do concerts here, music concerts, which is how we invented this process in the first place. Usually there's musicians sitting here playing. Lawrence and I will be singing later,
yes.
but much later. So if you would like to get on the if you would like to get on the mailing list for that, we'll pass that around. All they need is your email address, and anytime you want to come up here, they have concerts about once a month or so. So our next event is on April 23rd, so 4 weeks from today. This is Andrew Stuhlman. Science Blind is the name of his book. Why our intuitive theories about the world are so often wrong. So he's a developmental cognitive psychologist who studies how children develop theories about the world, like theories of physics, folk physics, folk biology. They learn pretty early on, if you drop something it falls, that sort of thing. But other things are not quite so intuitive, like evolution, for example. You don't see species changes. Dogs don't become cats. You don't see any of this stuff, so it seems counterintuitive. So he's going to be talking about that and what we can do about countering intuitive theories because science is not always intuitive, as we're going to find out today. June 11th, Walter Scheidel, The Great Leveler, Violence in the History of Inequality, from the Stone Age to the 21st century. So this is a Jared Diamond-esque picture. It appears that the only thing that flattens income inequality is war. So that's not, given our current state of inequality, that's not a promising thing. But anyway, we'll be talking about that. And then I'll start booking stuff for the fall again for September, usually dark in July and August. I was just talking to Robert Sapolsky, who has a new book coming out this summer called Behave. It's not a child-rearing book. It's a book. It's sort of a Pinker-esque type book about the history of human violence from the second before you act. He starts analyzing what happens to neurons and hormones and so forth, all the way to the last 1,000 years of human violence and how to get human behavior to change based on certain conditions. Anyway, he's one of the more interesting scientists of our time. And then this is our 25th anniversary of Skeptic Magazine and the Skeptic Society. So technically speaking, thank you. It was March of 1992 that we had the Amazing Randy as our first event at Caltech. In our first public event, our first issue of Skeptic came out that summer. Wow. So quarter century, here we are. So you have the honor of
that's amazing. I'm honored to do that.
Yeah, well, so we're happy about that. We're going to do something probably in the fall. Some big shindig. I have a PR firm that we're working with now to help bump our organization up to another level of public awareness, because we need to counter. We need alternative to alternative facts, which are, I guess, are probably real facts or something like that. Yeah, you may have heard. So,
or maybe just facts.
just facts. Yeah. So, our guest today, Lawrence Krauss, is a renowned theoretical physicist at the Origins Project at Arizona State University, where he also heads the cosmology department. He's the author of more than 300 scientific publications and 9 books. Including his bestsellers, The Universe from Nothing, and of course his first, The Physics of Star Trek. So I'll start with a little story that will probably go to your head, which you don't really need, but you have a lot of.
I need it every day.
I was on a road trip in Florida. I was speaking in Florida, and this physicist brought me in just to do the generic skeptic talk, and we were driving to NASA to give me the tour there. And so I said, he's a physicist. But not a public intellectual physicist, he just does physics. So I said, so we got to talking about all the public intellectuals that we see on TV, every physicist you've ever seen on TV. I don't want to name any names because then I'll get in trouble. Yeah. But I just asked them, all these guys say, I'm a physicist, I do physics, I'm doing science. And it's like, do any of them actually really do science? Because how would they have the time? They're always on TV. And he says Krauss is the one who does real science. So,
thank you.
And that's really making a difference. So, and I think this book, I read it twice now, and I see it as something of a sequel to A Universe from Nothing, in a sense that The Universe from Nothing was sort of the big picture. Here's the universe-size structures, and now this is the the other direction. I mean, when you write, do you think I'm going to write a sequel, or does it just pop in later?
try not to do sequels. I try. You know this, but there's a big tendency in your writing to write the same book over and over again because you are the same person. So I try to pick a vastly different subject. Sometimes ones that I don't know as much about, so I can learn. But this one, in a sense, really yes. Because I did think that there was this importance of trying to both represent the revolutions that have taken place in physics, which I've done in the large scales, but there are revolutions that have taken place in small scales that are equally unheralded. I mean, it's not just talking about them, but for example, one of the things most people think of in the 20th century, that the period from 1905 to 1925 is the big time because it was special relativity and general relativity and quantum mechanics and all that. But actually, I think historians in the far future may think of 1955 to 1975, which is a period no one's ever heard of, as being perhaps the most revolutionary period in 20th century physics. We went from understanding one force of nature to three forces. And in some sense, that is the sort of pinnacle of the greatest story ever told that I wanted to address, because I think it is an amazing intellectual journey. But it was also what I tried to do in the Universe from Nothing was take a question that religion had usurped. Why is there something rather than nothing?
Right.
Which is a physical question. And then address another question, why are we here? Which I also think in some sense religion has usurped. And the answers to these questions, and of course the why questions are never answerable because they presume purpose. Why questions, if they're going to make any sense in my opinion, are really how questions. And so I wanted to talk about the amazing fact, the result of this series of discoveries is that we are an accident in much more explicit and clear ways than we ever thought before. That not only is the universe not designed for us, but in fact, at a fundamental level, the universe, if it was designed, would be designed so we couldn't exist. Our existence is really an accident, as I say in the book, just like icicles on a window are accidents. And so that, to me, manifests the importance of the fact that there's nothing significant in a cosmic sense about our existence. That doesn't make our existence here and the individual existence we have less significant. We make our own significance. But I really think it's important to emphasize that these things that people die for are illusions.
Well, you mentioned treating nothing as a physical question, but it was always for thousands of years just kind of a metaphysical or theological. Or
yeah, I mean, and people still hate the fact that they say Krauss doesn't talk about nothing, and I say, I got in trouble because I made a joke at the beginning of the book. I said philosophers and theologians hate this because they're experts in nothing. But I didn't. But the point is that
they eventually accepted your apology.
Well, yeah,
sort of.
Well, the point is that I'm always amazed how the people who say that don't define what nothing is, and I worked very hard to define the nothing that I described. And if that's not their nothing, that's fine. I don't give a damn. To me, the amazing thing is that you can get a universe of 100 billion galaxies, each containing 100 billion stars, from no universe, no galaxies, no matter, and if that's not nothing, okay, but that's the miracle that isn't a miracle. And I think it's amazing that we have a plausible explanation of that. And then, as I say here, and I do think, and we'll probably get into it, that there is, especially...
But what you mean by nothing is a quantum field, right?
No, I just mean no space. I mean no universe.
Right.
So there's nothing. What I mean by nothing is that everything we see and that exists around us did not exist before. Now, did something else exist? Who the hell cares? Everything, our universe did not exist. And it came into existence. And I find that, so there are no quantum fields, there was no space, there was no time, there was literally nothing. And the example, and what amazes me is that people can buy it when I talk about quantum mechanics of light. So look at the light bulbs here. So there's these light bulbs, they're emitting photons. Those photons didn't exist. They weren't in the atoms waiting to be spit out. They were spontaneously created. That doesn't seem to bother anyone. But if gravity is a quantum theory, you can spontaneously create universes. And that bothers people.
So just back up. So because I quoted this in my Scientific American column, and I'm not sure I understood what I said.
Yeah,
which is often the case.
It's all, it never stops me. So
So the photon of light, it's in the atom, and it pops out. What causes it to?
There's no cause. That's what people don't like, the idea of cause. But quantum mechanics, I mean, physics says there's a probability, but there's nothing that caused the atom to emit that light at that instant. That's quantum mechanics. It's spontaneous. It's spontaneous emission, and people don't like having no cause. But in fact, in the case of a universe, it's even worse. And I didn't emphasize it too much in the book. But if space and time begin in our universe, if space and time begin when our space and time is created, that means there was no time before, and then the whole notion of before goes away, and then you have to change your thoughts about what cause means if there's no before. And I don't think we have a good answer, but that's what science is all about. It's, you know, what I point out is that we change our definition of things, and it's called learning. And it's not a bad thing.
I think this must be one of those intuitive theories of the world that I mentioned earlier, which is that you can't conceive of nothing, really. It'd be like trying to conceive of where you are after death. You can't.
Well, yeah, and so, but what I defined is the reason, and people say nothing's not a physical quantity, it's a metaphysical. What I said is, look, if nothing is the opposite of something, okay? And physics defines what something is, so the absence of something is really a physical question. And it is. I mean, to talk about nothing and not say it's a physical question it seems to me to be absurd. Some metaphysical concept that we make up in our minds is something we can think about, but it has no utility. And I therefore think, I'm very pedestrian, that if we can't describe it in terms that can be measured, then as a scientist, it's meaningless.
So you open the book with Plato's famous metaphor of the cave. So we're all facing this way. There's a light back there. Shadows are on the wall. We're all looking at the wall. And, you know, we don't really know what reality is. So, and your journey, your story, is how we've moved from the shadows into essentially the light. Literally.
Literally. I mean, it's a story that profoundly affected me when I was forced to read it in high school. Because I often say I grew up in Canada, so I was educated. And so I remember reading Plato and the cave, the allegory cave, hit me at the time. But when I started to think about this book, it hit me more, because it really is true that what science has done is take the shadows of reality. The world we see is the shadow of reality. And then the job, as he said, of the philosopher, mathematician, what we now call scientist, was to interpret from those shadows the reality behind it. And there's clear examples of that in the history of science. And that is the greatest intellectual journey we've ever taken, I think. And one of the hallmarks of it, and I use the example that I created for the cave, and I'm quite proud of that example. But of what they would see in the cave as things that are vastly different, that maybe have no meaning. And the people in the cave wouldn't understand the concept of length I talk about.
The ruler.
The ruler,
yeah.
And it really has clear application in physics. But more importantly, the hallmark of progress in science is when things that on the surface seem extremely different are seen as different manifestations of the same thing. At least in physics, if you wanted to classify progress, that's it. And I talk in the book about the progress of taking two forces that are very different, electricity and magnetism, and realizing they're exactly the same. Okay, and then if that led to Einstein to realize that space and time, which on the surface seem very different, are really exactly the same. And by that I mean one person's space is another person's time, depending upon the relative state of motion. Same with electricity. One person's electricity is another person's magnetism, depending upon their state of motion. And then leading to what was the sort of greatest unification in the last part of the 20th century, which was the realization that two fundamental forces in nature that are vastly different are really the same. And moreover, they're the same because of an accident of a field freezing in the early history of the universe. And I will, if you will indulge me, to give the example that I really like, this ice crystal example. Now, those of you who live here, I'll have to imagine what ice crystals are. but on other places, on windows, there's beautiful patterns. I actually put a picture in there for it to guide the Los Angeles reader. And they're beautiful. But if you try to imagine what people who lived on one of those crystals would discover if there was a civilization along the spine of one of those crystals, the physics would be very different along that direction than in perpendicular directions. And physicists would come up with an explanation of the physics, which would make that direction special, because it would be. And then theologians would come up and say that direction was determined by God, it was important. And there'd be wars fought over why that direction versus that direction, and people would die, and it would have special significance. But when seen from the outside, it obviously has no significance. And for us, it's exactly the same. The field froze in a way that made our existence possible, that made electricity and magnetism different than the other forces in a way that allowed us to live and makes it look like the universe is designed for us and fine-tuned for us, but it has no real significance. The field could have frozen in a different way, and we wouldn't be here.
So it would be wrong to say it would just be a different life form. There'd just be no matter. Right?
There'd be no matter in that universe, absolutely. But can I say that there'd be no kind of intelligence? I don't know. Freeman Dyson and I, for many years, had a long scientific discussion, the debate in scientific literature about what kind of life forms could exist. But we wouldn't. The universe would not be not set up for us. And if it had been different, there'd be different configurations of forces. And you're right, matter would be massless, and it's hard to imagine life if there aren't stars and galaxies and planets and aliens. But so one could say that, yeah, life is only possible because of that accident. But I think since I don't know all the possible ways that consciousness could arise, I'm not willing to say, I'm not willing to make categorical statements about things I don't know. I try not to anyway.
Now, why would this not feed into the theologian's argument that you mean to tell me this is all an accident? Come on, that just seems so improbable. That intuitive theory of the world, it just seems improbable that an accident could lead to this. Therefore, there's a designer outside of space.
Well, it happens all the time. The illusion of design is prevalent. We're hardwired to look for design. We're hardwired to have teleology. We want there to be a why in some sense for everything, and we're hardwired to look for design. And there are lots. I give lectures on lots of examples of things that look like they're designed. You could say, well, human architecture is obviously designed. Like Buckminster Fuller domes. When I was growing up, every hippie had one, and they're obviously designed. But then you take soot, and there's Buckminster Fullerenes, carbon-60, which is a geodesic dome, and there's nothing less designed than soot. So you have to be really careful when you claim design. It's an amazing claim, and you've got to have evidence for that. And I think the operational argument should be that there's no evidence for design. You have to prove it in some sense. And for weird accidents, accidents happen, and then all of us ascribe significance to things that are accidental. And Feynman used to, I wrote a book about Feynman, but he would all the time. In fact, I saw his van because of you. I now remember.
That's right.
But Feynman would go up to people all the time and say, "You won't believe what happened to me today. You won't believe it happened." And they'd say, "What?" And he'd say, "Absolutely nothing." Because every time something significant happens to you, you dream thousands of nonsense dreams. And then one day you dream a friend breaks their arm, and the next day they break their leg, and you go, "Oh, cosmic." And it's just an accident.
I always liked his license plate example. You can't believe the license plate I saw. It was QL7962.
Yeah, who would have thought?
Yeah, who would have thought it could have come out like that?
Yeah, exactly. And so I think there's a natural selection argument. How could this universe be so fine-tuned for us? And they realized, and it was Darwin in The Conquest of Life who did this in another sense, but I think we do it in physics now, to say the universe isn't fine-tuned for us, we're fine-tuned for the universe.
Yeah.
We arose in a universe that allowed us to arise. And it would be amazing if we arose in a universe that didn't allow us to arise. That would be worth a book or two. So it's not surprising that everything seems so nicely tuned for us. And it was the genius, I think, of Darwin, at least, in the case of biology, that reflected that. And now the kind of physics I do is maturing enough to the point where we can at least honestly address that question. I don't think we could have 25 years ago, and I don't think I could have written those books. And I don't think I could have written The Universe from Nothing before I did. And this one, of course, the pinnacle of it, in some sense, is the discovery of the Higgs field, which changed everything in my mind, because I actually thought I didn't believe in it. So I don't think I could have written this book. Someone asked me the other day, could you have written it a decade ago? And the story was still amazing, and still, in my mind, the greatest story ever told so far, and that's the best part of the title, the so far part, because the story of science gets better every day, and tomorrow it'll be better than today. It changes, unlike the story written by illiterate peasants 2,000 years ago before they knew the Earth orbited the sun. That remained constant, which is one of the reasons that it's so boring. This story gets better all the time, and the reason it gets better is not because of humans, not because of human inventiveness, but because of nature. We get driven forward by new tools that open up the universe and bring us kicking and screaming to the reality. The great thing about this story is that, I try to make it a story, and there's lots of neat scientists, and part of the fun for me was to really learn the history in more ways than I thought I knew. who go down blind alleys, and red herrings, they have prejudices, and scientists are people. People don't realize that, but scientists are people. They have prejudices and biases, and scientists are prejudiced and biased, but the science overcomes that. And that's the wonderful aspect that I wanted to celebrate, is somehow nature forces the scientists to change their mind and accept things that would have been crazy. And that, by the way, is there are lots of lessons I think this book has for the current miserable situation we're in. So I think looking at what I think is humanity at its best, which is the story I think I've told, has real lessons for looking at what's happening now in our society, which is, in my mind, humanity at its worst.
So you feel that obviously there's progress in science. You're not an end of science kind of guy.
Oh, it's so presumptuous to claim that.
But with the opening story of Plato's cave, to the new ager today who may say, like our mutual friend Deepak Chopra, it's all it's all shadows. Yeah. It's all shadows still because we don't really understand consciousness. And,
well, I mean, consciousness. Some of you throw in when you want to because it has no meaning right now. I mean, we don't understand consciousness. It's an amazing concept, and that's why, by the way, I do physics, because it's so easy. It really is. It's low-hanging fruit. The consciousness is a problem that's going to take a lot longer to solve.
But I mean, how do you know that we're still not looking at shadows?
We are.
Oh, we are. Okay.
That's what's great. That's why it's so far. We've discovered fundamental realities about our universe, but we haven't discovered all fundamental realities. And each time we make a new discovery, more questions arise than answers. That's what makes it so wonderful. So no, I'm not claiming in any sense that this is a complete understanding. And if you ask me whether we'll ever have a complete understanding, I'm dubious of that. To quote Feynman again, it's fine with me if the universe is like an onion with an infinite number of layers, peel it back, and all he wanted to do and all I want to do is understand a little bit more. And the search and the new, it's like saying culture will end.
Right.
Because no, it's really an important thing. Because people, for me, one of the sad part, not sad, but unfortunate parts of science in a way is that it produces technology. Now, it's unfortunate because we wouldn't be here and we probably wouldn't be alive if it weren't for the technology that science has produced. But then when I talk about the kind of science, I do people say, well, what good is that? It didn't make a better toaster or anything like that. But the point is, the real value of science to me is the value it has that's the same value as art, music, and literature, which is to change our perspective of our place in the cosmos, to cause us to rethink ourselves, to get uncomfortable, which I once said and almost regretted, but I don't. It's because if you're never outside your comfort zone, you're never progressing. And to say that science, will end is like saying culture will end. It seems to me there's always going to be ways to go out of our myopic worldview and see the world in a new way. And that's the great legacy. That's what would make America great, is to not get rid of. I just wrote a piece, and this is not my line, that's a wonderful line, but to not, Robert Wilson was the first director of the Fermi National Accelerator Laboratory, a particle physics machine in the United States, and he was asked by Congress in the 60s if it would help aid in the defense of the nation. And he said, no, it'll help keep the nation worth defending. And I will delve into politics for a moment to say something, because I feel strongly about it at the moment. Right now, the story I tell here, which is amazing, is a kind of physics which is supported by the Department of Energy in this country. It's the only, what people don't know is the Department of Energy supports almost all physical science research in this country. It's the chief funding agency. So it's being cut by 20% in the present budget, by $900 million. The National Endowment of the Arts is being cut completely. The National Endowment of the Humanities, Corporation for Public Broadcasting, the Institute of Museums and Libraries. You add all that up, it's $1.62 billion. I added it up the other day. In the same budget that's cutting that is $2 billion for the first payment on a wall with Mexico. So the question is, you want to defend the country against these supposedly invisible hordes? By what do? You get rid of what makes the country worth defending. Because what will make us great is the legacy we leave for our children, the progress we make in our ideas and our culture. And that's what's important. And that's what I see as the real benefit of science, and why it isn't divorced for culture. Of course it produces technology. Of course it's responsible for the current economic well-being of this country. And that's great. But I think the cultural aspect isn't sufficiently appreciated.
I'm still not sure.
That's my tirade.
I'm still not sure how you feel about this.
Yeah. That's right.
Well, let's pull back for a second
Yeah, sure.
and look at sort of the zoo of forces and particles and so on. Just
Let's talk
get
science.
everybody up to speed. So you have gravity, electromagnetism, weak and strong nuclear force, and then you have atoms, and in the atoms are the electrons and neutrons and protons, and then you keep boring in, you get quarks and so on.
Good.
So,
A.
now, when you say something like electricity and magnetism are the same thing, they're instantiations, two different instantiations of the same thing.
Well, no, what I mean by they're the same thing is that it depends upon how you look at it. It's not that they're two different representations of the same thing. One person will call a force that they measure in a laboratory an electric force. Another person can look at that same force, and it turns out in this case, if they're moving, in their laboratories moving relative to the system, will measure that same force and call it magnetism. So they really are the same thing because different people will label that same phenomena magnetism or electricity. And in fact, I think I talked about it in the book. I'm kind of amazed in a way that that's not represented. It's something I thought about. But people, if they had thought about it correctly, early experiments that were done before Michael Faraday, in a sense, should have made them realize that magnetism and electricity are the same thing. But of course, it's easy with hindsight to say should have. That's one of the things I think in the book that I find great for me, because I wanted to take these physicists by their shoulders and shake them and say, don't you,
Yes.
It's all here, you got the answer. It's not going to take 20 years, it's all there. But everyone is, and science progresses in fads, and as I say, incorrect thoughts eventually get corrected. But they really are the same thing. And space and time really are the same thing. Because what Einstein ultimately showed, and it wasn't Einstein who realized it, it was his math professor, one of the people who sort of tolerated Einstein, Hermann Minkowski, who realized 3 years later that the consequence of Einstein's discovery was that space and time were tied together. And now, if you think about it, the reason different observers moving relative to each other measure things to have different lengths and their clocks slow down and all the rest is simply because they're seeing sort of different rotated three-dimensional slices of a four-dimensional space. So it's kind of in a more complex mathematical rotation. But if you see a rotation, then if I have the x and y axis and I rotate, then what was all y has now got a little bit of x. Okay, I hope you get that. Okay, and the same thing happens in our four-dimensional space-time. When I'm moving with respect to you, what was all space for you ends up being a little bit of time for me. And it really is true. Things get, in a sense, rods get shorter, but at either end of the rod, the clocks are ticking out of sync with each other. So the rod now has extension in time that's non-zero, but shorter extension in space. And when you combine the two together, its four-dimensional length remains exactly the same. So it could have been the theory of absolutes. In four dimensions, there are absolute quantities. And it's amazing to think that we humans, and that's why I used the Plato example, because if you're looking at the shadows of reality, you're seeing two-dimensional shadows of a three-dimensional world. And those beings would not understand a three-dimensional world, but a mathematician might explain to them that what they're seeing is a consequence of a three-dimensional world. And what Hermann Minkowski and Einstein eventually told us is we're seeing just this projection of a four-dimensional world, and it's really weird for us because time seems so different than space, but they're really not different at all.
Now, some of this could not have been figured out centuries ago because either the math wasn't there or the technology of, say, particle smashers to do that, right?
Yeah, in every case, Einstein wouldn't have been Einstein. Well, he would have been Einstein, but you wouldn't have heard of him if he hadn't been after Maxwell. And it builds. That's the other thing about this story that makes it important. It is a story with a lot of people involved and a lot of science involved, and usually baby steps and wrong turns, and always, essentially, always driven by experiment. I mean, we theorists have better press agents than experimentalists, I guess, because people know Einstein and Newton, although Newton did experiments. What's really forces the direction is not people late at night having revelations. Revelation, in my opinion, has never led to any knowledge. Okay, I'll say it again. Revelation has never led to any knowledge.
Depends what you mean by revelation.
Of course. I mean, creativity has led to knowledge. But the revelation, what I mean is something that comes out purely out of your mind without being related to your experience.
Well, yes, of course.
And I know
right.
in your philosophical way, you're going to say, well, that's okay, I would call revelation when I suddenly realize when I have an aha experience.
Right.
And that science is full of aha experiences, but they're all based on observations at some level. And certainly it's the observations that have driven physics forward. And if you you'd locked physicists in a room in 1915 and let them out in 1975, they'd be older and the room would smell like hell. But the world they would have come up with, no matter how creative they were, would have not resembled the world we live in at all.
Right. Well, we know from research from cognitive psychologists on creativity that the people that are most creative in their fields are completely steeped in the field itself. Musicians have vast collections of records and they listen to music, and novelists read a lot of novels. And so this is one answer to the outsider that writes you. I'm sure you must get even more of these than I get. Yeah. I've been working on this theory of physics every weekend, and if you help me with the math, I'll share the Nobel Prize with you.
Yeah, I get that.
And I send them to you. So I'm not a physicist, but my friend Lawrence Krauss would be really interested in it.
Yeah, exactly. There's the famous, there's many famous stories about that, where people send the nuts to other nuts, and they say, I talked to that guy, but that guy's a nut. Well, anyway, but
actually, the best one, Margaret Wertheim collects these. She's a science writer, and she has a book about all these alternative theories. Physics on the Fringe, as it's called.
Yeah, I know it, but the point, there's a real serious. I get these letters every day, and they usually begin, and I mean every day, and it usually begins with everything you think you know is wrong, and half of those are political. But the other half are physics. And then they always say, and this is what amuses me the most, here's the logic that then proceeds. They say, everyone thinks I'm crazy. Everyone thought Einstein was crazy.
Right.
Therefore,
yes.
And then I know to hit delete. But what they don't recognize, and all of these things have valuable lessons, I think. You can make fun of it. But what they don't realize is actually something that I think most people don't realize. And one of the reasons science isn't taken seriously by many people is that people think that scientific revolutions do away with everything that went before them. So everything we think is true today will tomorrow be wrong, so why bother learning? Science is a fad. Tomorrow the truth will be different. And that's not the way science works. What satisfies the test of experiment today will always satisfy the test of experiment. Newton is just as true today as it was when he came. Sure, at the extremes of scale with general relativity has changed, and at small scales quantum mechanics, but for throwing baseballs and cannonballs, Newton will always be true. Whatever we discover about quantum gravity, if you take a ball, it's always going to fall and be described by Newton's law. So whatever new discoveries we make in science cannot throw out the aspects of science that survived the test of experiment. And I used Einstein as a test case here, because what Einstein didn't do was throw things out. His genius was to realize the two fundamental pillars of physics, turns out Maxwell's equations and Galileo's laws, were inconsistent. But they were both true. They both were true, so you couldn't throw them out, but they were consistent with one another. That was part of his brilliance. And then his real brilliance was to say, I'm not going to throw either one out, I'm going to figure out a way to make them consistent. Now, I don't have time to tell you how, but I certainly did have time to describe it in the book.
Read the book.
Yeah, no, I think it's important. That story I like importantly, because another problem with the way we teach science, and there's so many, is we teach it as if, first of all, if it's a bunch of facts, which it isn't. It's a process for deriving facts. That's vital. Maybe we can get into that later. And Skeptic magazine's a big part of that, I think. Beyond that, I'm trying to think I know I had a point I wanted to make.
Well, I was kind of just driving at some of the heroes in your story certainly stand out above the rest of their colleagues at the time. But they're steeped in their science. And
they're definitely
steeped. They just sort of push just a little bit more.
But some of the heroes of my story get it wrong. I think it's important that the people I talk about there who are great scientists often have helped tremendously by pushing an incorrect theory long enough to see that it was wrong.
Right.
And they don't get credit. But sorry, I'm going. I know where I was heading before, but anyway, go on.
Yeah. Well, then, okay. So back to where we began with, the 1905 to 15 seems like the big, but that was mostly the theory. Did it take?
Well, it wasn't just theory. Okay, Einstein was driven by experiment by Maxwell. Einstein was driven by Maxwell, which was theory, but the discovery of electromagnetic waves.
Right.
Quantum mechanics was driven by the weird properties of light, again. And light plays a role throughout this. That's why I begin the book with Let There Be Light, because it's a central part of much of our understanding. Quantum mechanics wasn't invented by people who thought, hey, I'll make the world neat. It was, there were paradoxes, experimental paradoxes, that drove physicists to this crazy assumption, which in fact Einstein, even though he was central in creating the field, eventually couldn't accept himself.
Right.
And that's another thing about science that's often the case. Scientists are lucky. You're very lucky if you make contact with nature once, in a sense. I mean, of course, we all make incremental developments, and that's fine. But if you do something dramatic and you make contact with nature and discover something new about nature that wasn't there, it's an amazingly fortunate circumstance to be in. But it's interesting to see how physicists, somehow there's this cognitive non-dissonance with nature that somehow for a while, they're right in tune with everything, and then the field moves on. And as Max Planck once said, physics proceeds one funeral at a time, because the scientists die and the science proves up.
But what I'm getting at is what was special about the 60s and 70s that was not available to the Einsteins?
Interesting. Well, a host of experiments, first of all. The onset of experiments in particle physics. First, the discovery of the decay of the neutron. Things were really neat until the neutron was discovered, because there were two forces in nature. There was electricity and magnetism and gravity. And more or less both had been explained at some level. Gravity, the fact that quantum gravity didn't really matter in the early days. Electricity and magnetism was a great theory, and both those are really the two forces that appear to affect the world on all scales we can measure. So it was done. We had a great, great. We could go home. And then this weird discovery of the fact that the neutron is unstable, which should surprise some of you since you're made of neutrons, and the lifetime of a neutron. And the lifetime of a neutron is 10 minutes, and we have been going on. You will understand.
So we are decaying.
Yeah, well, I mean, no, we're not, happily, because it turns out we've been around for more than 10 minutes. Some of the people here may wish it wasn't that case, but that's not a miracle. That's an amazing accident I talk about in the book. But the discovery that neutrons decay began to make the world messier. And then new particles were discovered, and the world got so messy that people were willing to give up the fundamental theories they had. And in the 1950s and 60s, even though, as I point out, many of the key ideas were there that eventually led to the right direction, it was such a morass that people were willing to give up basically almost everything that we understood, and went in a lot of direction. It was the birth of string theory was in the 1960s, because it was developed because they thought the conventional picture just couldn't work to explain the strong interaction. And they developed this theory, which was wrong then, and just like it may be wrong now. and because they said maybe the conventional picture of elementary particles just doesn't work. There was, out of Berkeley, of course, there was a Zen theory of, it was called the bootstrap model. It said elementary particles are not fundamental. This particle is made of this particle, but this particle is made of this particle. It's sort of the sound of one particle clapping, and it sounded great. I mean, it made no sense, but actually it was a leading idea in physics at the time, because people threw up their hands and couldn't really understand the picture. And it's amazing in that 20-year period that we went from understanding electrodynamics, quantum electrodynamics, a theory that Feynman and others helped make the best theory in nature, to understanding 3 of the 4 forces in nature exactly, and understanding every experiment you could do. And not only that, but ultimately understanding the mathematical symmetries, the underlying aspects of space and time that seem to govern all forces in nature that we can see now. All of that was discovered, and there's this, I talk at length about this thing called gauge symmetry, which is a central idea in modern physics, but you've probably never heard of it because it's very subtle and difficult. And actually, one of the things I'm kind of happiest about in the book is that I spent a long time trying to think of how to explain gauge symmetry, because it is so subtle but so important. And to tell you the truth, my editor wanted me to get rid of it all and I said, no, because I want to tell people about the real universe, and this idea is so central. So I spent a lot of time, and I think I give an example of how to understand gauge symmetry. And what was neat for me, and this is true of most of my books, is because I learn stuff when I'm writing books, which makes it worthwhile for me. And let me make it clear, I generally write books for me, just like I generally do science for me. I don't do science to save the world. I do science because I enjoy it. Okay, and I think most scientists, if they're honest, will say the same thing. And if you don't enjoy it, you're probably not doing well at it. Now, I think there's a reason for writing books, and I think it's useful for me to take time out of my science to do that and also to speak. But it's a pleasurable experience, and I gain something from it. And in this case, I actually understood gauge symmetry afterwards in a way I'd never understood it before. And I actually kind of realized that for me, the picture I invented, which is the way I try and describe it in terms of pictures, because I think it's easier for people to understand, made me realize I could have discovered the mathematics which eluded people for 20 years just from that picture. So if I developed that picture at the time, which was before my time, I could actually have predicted the mathematics, and I never saw that before. So anyway, there are aspects of understanding the world that were developed during that period, which now are the basis of those principles, form the basis of the theories that we're trying to invent in the future. They form the basis of string theory, but they also form the basis of grand unification and all of the approaches we're taking, which could be a dead end. And we don't know. And that's what makes it neat. And if the Higgs hadn't been discovered, this beautiful picture, which was, I thought was a little slippery and slimy, that's why I didn't believe it, could have, this whole intellectual house of cards that had been years and years of people's lives and experiments, all of it could have come tumbling down. And that's the beauty of it, being able to put yourself out for an idea that you're willing to realize could be wrong. And then accepting that it's wrong. That is so beautiful. And I wish we as people and in our society were willing to say that we can have ideas that we think are wonderful, but we should be willing to throw them out if they don't agree with reality.
Are these four forces all instantiations of the same thing?
We think maybe.
Is that what the Higgs has to do with?
No, the Higgs gives us an example of how two forces that seem very different could be the same. Now, right after that was developed and understood, it didn't take long before people, with actually 2 years before people, a number of people, I talked about Shelley Glashow, Howard Georgite, and then Steve Weinberg and others, Owen Quinn, recognized that it was conceivable by exactly the same kind of mechanism. 3 of the 4 forces of nature that were now understood could be unified. And that became known as grand unification. I was just reminded by 2 of those people that they didn't call it that. They didn't want people to think that they were pretentious enough to call it grand. Other people did. But that would mean, and all of the data suggests still that 3 of the forces in nature really are unified. Okay? And then there's a hope that the 4 of the 4 forces in nature would be unified, and that was really the motivation of string theory. And it seems when we look at nature at more fundamental scales, in that sense, it becomes simpler. That things that are different, as I said to you before, things that are on the surface, are we being attacked?
Yeah, this is the NSA.
Oh, yeah, okay. Things that are...
Ooh, those are military helicopters,
yeah,
okay.
All right. Everywhere I go, they follow me around. It's awful. But
what is it you know
I can't
tell you? Telling us?
I can tell you, but I have to kill you. But that example, once again, of things that on the surface seem different, end up being different reflections of the same thing. And what is also important to realize is that physics is like Hollywood, or publishing for that sense. If it works, copy it. Okay? Halloween 23. I mean, and so we physicists say, if this theory works, if this picture works here, let's apply it there. And let's keep applying it. And so we push to the end until we discover that maybe we're going on a dead end. And so this notion of grand unification is pushing forward the same ideas that worked so well for the electroweak theory. And it could be wrong. The data, what's neat is in our lifetime, we may know the answer. And I think that's amazing too. The Large Hadron Collider, which I argue is, well, not I, but people recognize is the most complicated machine people have ever built. And I call it the Gothic Cathedral of the 21st century because it is like Gothic cathedrals were in their time. It's not over. It discovered the Higgs, much to our surprise, because actually a lot of us thought it would discover other stuff first. A lot easier, this thing called supersymmetry and maybe the nature of dark matter. And it's not turned off. And it's going to run for another 10 or 20 years. And we hope it will discover things that will push us forward, because every time you make a discovery like the Higgs, a profound one, it raises more questions than it does answers. Why the Higgs? Why is this invisible field everywhere in space? Why did it occur when it did? Why did the universe freeze that way? We don't have the answers to those questions. And so we hope, and what's clear is we got a lot of ideas. Theorists have a lot of ideas. And before the discovery of the Higgs, I used to say we were like, and it's appropriate to talk about this in California, you know those isolation tanks used to be especially so big in the 60s.
Floating
yeah,
tanks.
yeah, yeah.
They're back now.
Yeah, I know they're back. I've been in one. It's kind of fun for a little while.
It's a drug-free and legal hallucination.
Yeah. And exactly, if you're in one of those things, sensory deprivation leads to hallucination. And I used to say that's what physics was for about 30 years, because we were looking for new directions in fundamental particle physics from the 1970s, and we had none, essentially, until recently. With the new Large Hadron Collider, we had one or two, but mostly and therefore the physics literature is filled with hallucination, which some people call theoretical physics at some level, because I get paid to speculate as well as to explain. And so there's lots of ideas of what might be next, because we had a lot of time on our hands. But most physical ideas are wrong. Most of what we come up with is wrong. If it wasn't that case, anyone could do it. And when you read, therefore, in the literature, and not the scientific literature, but even the scientific literature, when you read in newspapers, oh, this is the greatest thing since Einstein, be skeptical, because it's probably wrong.
We had Lisa Randall and Janet Levin here as guests earlier last year, and dark matter, of course, was subject of that. What do you suppose? What is your throwing out your best hallucinatory guess while you're floating in the tank? 95% of the universe, we don't know what it is.
Well, I've thought about dark matter for a long, long time and worked on it and made proposals for what dark matter is, and happy to say that I actually proposed the experiments now that are looking for dark matter. So I have a dog in that fight.
Yeah.
But it depends on the day. I'm kind of agnostic about it. I do think the best candidate, the most well-motivated candidate, is still what I would call the lightest supersymmetric particle, which may be accessible at the Large Hadron Collider. Because the theory, if it's right, the theory naturally falls in the range that produces dark matter. Although it's getting squeezed at the Large Hadron Collider. We thought it would be those particles would be discovered right away. They haven't been seen. And if in the next years they're not seen, that theory will become much less attractive. The other side of it, there's a theory, a totally different kind of particle, actually, which was proposed by my friend Frank Wilczek, called the axions, because he always wanted to name particle after laundry detergent. And it's a very different particle, and in some ways it's the reason it would be dark matter is so elegant and beautiful that I find it very attractive, but it's not. But while I suspect the principle that leads to axions does exist in nature because it explains something fundamental about particle physics, that principle doesn't require those particles to be dark matter. So it would be kind of a fluke if they were. But those are two good examples, but it's equally likely that dark matter could be none of the above. What I find less likely, frankly, although people love to talk about it, is the possibility that the dark matter is not dark matter, that it reflects the fact that gravity is not what we think it is on large scales, which is a far more radical claim.
Is that quantum gravity? Or
No, quantum gravity we think of at small scales.
Okay. All right.
It's the claim that maybe there's large extra dimensions that somehow are affecting, but somehow that gravity changes its nature on large scales. But there's no fundamental reason why it should on the scale of galaxies. Moreover, dark matter is observed in lots of different scales, so you have to stand on your head to make it work. And it seems to me much less, not only much less attractive, but much less radically conservative, as again a friend of mine says, in the sense that dark matter is not too surprising. It's really not surprising that most of the matter in the universe is invisible. If you think of it this way, the number of photons in the universe for every proton, the particle that makes particles that make us up, is about between 1 and 10 billion to 1. There are 10 billion photons, 1 or 10 billion photons for every proton in the universe. So by number, we're very rare. Turns out photons don't have mass, so they don't dominate the mass of the universe. But they're produced in the early Big Bang. And by the 10 billion, that's the number of particles in the cosmic microwave background radiation that we see permeating space. So it's not so surprising there might be other particles that are produced that are far less abundant than photons, but have a mass and dominate the mass of the universe. In fact, it's almost any time you extend the standard model of particle physics, it's almost impossible not to get particles that are dark matter. It's not a very radical assumption. And indeed, if you look at it, even the photons, nothing is more observable than light. in general. But the photons from the cosmic microwave background weren't discovered until 1965, even though there are a billion of them for every photon, and they were discovered by accident. So the most visible thing in the universe that permeates all of space, there are 300 cosmic microwave backgrounds in every square centimeter of this room right now from the Big Bang. Yes, really.
Say it again.
There are 300 cosmic microwave background photons in every cubic centimeter of this room. 10 to the 13th of them going through every square centimeter every second.
I was feeling warm. And that's
Well, and so they're everywhere. But we didn't discover them until 1965 by accident. So it's not surprising there could be other stuff we don't see.
Is this the kind of thing that CERN could continue to do, or do we need a bigger particle accelerator?
We don't know. We don't know. It'll depend. I mean, that's the point. We don't know what they're going to... People always say, what's the next big thing? And I always say, if I knew, I'd be doing it. But,
Right.
but that's why it's turned on. And the really neat thing is, for example, if they are these supersymmetric particles, or particles like them, then there's a race. Because CERN could produce them in little mini versions of the Big Bang when it has these collisions. Or we could observe them directly, the ones that came from the Big Bang, and we built these detectors, the kind that I and other people have proposed early on. Build them underground and look for them. So there's this race right now between CERN and these underground detectors that are being built, and being bigger ones being built because we haven't seen anything underground. And who knows what'll win that. But it's kind of nice that there's these sort of two different ways for looking for that kind of dark matter and other kinds of dark matter. And so we don't know what will happen. And they could all see nothing. But that doesn't mean they're not there. And it doesn't mean we're wrong. And it doesn't mean there's a God. I mean, I often say that lack of understanding is not evidence for God. It's evidence for lack of understanding. And we always make excuses when we don't understand stuff like, oh, we'll never understand it. You know, look, scientists haven't found this, or scientists don't understand love or consciousness. We'll never be able to understand it. But I find that statement incredibly pompous. Mm-hmm. Because if you say, we'll never understand this, it implies you understand it at some level. So you know enough to know that we'll never understand it. And how can you say that unless you have some knowledge that we don't have?
Well,
we don't know till we try.
There's the known knowns, the known unknowns, and then the unknown unknowns, things we don't know that we don't know.
I think I quoted Rumsfeld.
No, you didn't quote him in here.
Okay,
I think that was your previous book. But I mean, it's a nice, simple exercise in epistemology. How would you know what you don't even know?
Yeah, yeah.
So we...
and the universe has told us that, in fact, we get the reason physics isn't... I don't want to demean philosophy, because I do value philosophy. Just not certain parts of philosophy. But the reason, one of the reasons it isn't, is that those kind of questions, the arbiter of truth in that way is not us. It's empirical reality. So the unknown knowns are, what's great is we get helped because we open new windows in the universe and we get told what those are. We don't invent them. Nature suddenly throws us a curveball. So we're so helped by that. Mm-hmm. And the imagination of nature is so much greater than the imagination of human beings. And that's why science is so much more interesting to me than science fiction. And I like, science fiction has been good to me too, the physics of Star Trek and stuff. But nature, we discover things that no science fiction writer would ever come up with, ever. Because it doesn't rely on our imaginations. Nature suddenly presents us with this picture, be it quantum mechanics or dark energy, that seems so unbelievably ridiculous that no one would have taken it seriously if nature hadn't pushed it.
Maybe you can explain to me what it means to have a mathematical universe. Max Tegmark's thing.
I'm afraid I don't think much of it.
Okay, I'm not even sure I grasp what it's supposed to mean.
Well, I don't.
But I mean, there's certain mathematical principles that are true. They're not matter. They're not energy. They exist.
Mathematics is a language.
Are they?
No, look, mathematics and physics is a model of reality. It isn't reality. Okay?
Right.
So mathematics is a tool and a language that turns out to be incredibly good to model reality. But to give it something more than that is something I don't understand.
Right.
To make a claim for it beyond that. What is amazing, and we don't really understand, although we have much better understanding of that than when Eugene Wigner first wondered why mathematics was so efficient about describing reality. But what is amazing is that when new mathematics is discovered, we find almost always that it has some applicability in describing the physical universe. Even the mathematics that at one time seems esoteric, later on seems applicable. So mathematics is very rich as a way to, it's the best tool to understand the real world. But I guess too pedestrian to think that there's, I do accept, I was going to say believe, but I try never to use that word. I find it highly much more likely that there is an objective reality. And I find, and every mathematical model is a model, and every physical model is a model. Every law, no, there's no such thing as a law of physics that's absolutely true. All laws of physics describe nature over restricted ranges of scales. Even quantum electrodynamics, the best theory we have, describes nature over a restricted set of scales. So even the best theories we have are only models of reality over small regions. Now, it is true that if some people argued the string theory might indeed be a theory of everything, which is an awful phrase, because it's really a theory of very little. No, really. And as one of my friends, as Frank Wilczek likes to say, he'd much rather, he doesn't want a theory of everything, he just wants a theory of something. But it is true that because of its properties, it actually could be the first theory that was sort of described nature over all scales, which is one of the reasons I think it's suspect in my mind. But no physics. In one of my books, Fear of Physics, I talk about what scientific truth is. There's no such thing as absolute truths in science in any way. Even our best theories are not absolutely true. They're absolutely true over some range of scale. And beyond that, they all break down. And so every theory we have is just a model of reality. Reality is much richer, and our job as physicists is to try and get better and better models. But I think it's pretentious to claim that that our models are the same thing as reality.
So
in my mind.
a law of nature exists really only in human minds.
No, I don't want to. No, I think
you don't want to go that far.
No, I don't, because a law of nature describes.
But
how
the law
nature
part, not the nature part.
No, nature observes that law, but only over some restricted range.
Right.
So it is a law. It's every sense that we think. Gravity works the way Newton described over a certain range of scales. And general relativity describes it over a much larger range of scales. And those are laws, but you know what I mean by laws is that what physics can't do is say what's true. What science does, and I'll extend it beyond physics, but what science does is say exactly what isn't true. Science can define unequivocally what's false, because what disagrees with experiment is false. And it's false today, and it'll always be false. So we can describe absolute falsehoods, but not absolute truths. And it's kind of like Sherlock Holmes. You get rid of all the things that aren't true, and eventually what's left over has more likelihood of being true. It's like the dog in the night. And so what we do is rule things out, and what our laws tell us, in some sense, is what isn't possible. And that's why symmetries of nature are so important, because what symmetries tell us is they restrict the playing field on which physics can happen. And what we've done, the big change in physics over the 20th century that is also not appreciated, that I try and talk about in the book, is we've turned away from forces and laws to symmetries, because symmetries restrict what's possible. Let me give you an example. Another way we teach physics badly in high school and university is we say the law of conservation of energy. Energy is conserved. And you got to write that down, and it's like the Ten Commandments. And kids are supposed to take it down as if it's an act of faith, which is something none of us should ever have. But that's not what it is. We now understand that the law of conservation of energy is a direct consequence of the fact that the laws of physics don't change with time. If and only if the laws of physics don't change with time, then there is a quantity called energy which won't change. So what now you can do is look to see if the laws of physics change with time. And it's much more
Do you mean like in the early universe versus now, or
in the early universe, all throughout the history of the universe? And I've written scientific papers showing that you can show that gravity cannot have changed from the time the universe was 1 second old to today. From the time of the universe was even earlier, you can show that electromagnetism has not changed in any way by 1 part in 100,000 between then and today. But if the laws of physics did change with time, then energy wouldn't be conserved. And you can now understand that, okay, it makes sense to me to accept that it's highly likely that energy is conserved, because the laws of physics don't I don't wake up tomorrow and suddenly discover it's different for me to get out of bed. Let me give you another example.
Well, you might.
Yeah, I may. It's called getting older. But let me give you another example. The fact that the laws of physics don't change from place to place implies that something else is conserved called momentum. Again, something else we prescribe in high school physics. But it's really people are really much more willing to accept that the laws of physics in Los Angeles are not different than they are in St. Louis. And if they were, it'd be awful, because you'd have to take Physics 101 in this building, and then Physics 101 in that building, and you'd have to take it all over the place. So again, the fact that laws of physics are the same everywhere in the universe implies this conservation of momentum. And by the way, we don't accept it on faith. We determine that it's amazing to us that we can show that the laws of physics are the same in distant stars.
That word is not good. Confidence or experiment or high probability.
Yeah, I mean, and it is true that we make assumptions. And Einstein, for example, made the assumption that the universe was more or less the same everywhere. It was an assumption of simplicity because it allowed him to solve equations he couldn't have solved otherwise. And came up with a simple cosmological models that resulted on those assumption that the universe was the same everywhere. And we've discovered that that's true. It didn't have to be true, but it is. And it is not. We actually measure, amazingly, that the laws of physics are the same in distant galaxies than they are here. We measure the spectrum of the atoms is identical, and that depends both on quantum mechanics and electromagnetism. And so we can show that those forces are operating the same way in distant galaxies as they are today. We don't take it on faith.
I want to be sensitive to our time, so we have plenty of conversational time with the audience. So let's just move to the lightning round. And just get your, quick opinions on some of our mutual interests. You're a member of the Union of Concerned Scientists.
Yeah.
You're the guy, one of the guys that moved the doomsday clock.
I'm chairman of the board of that.
3 minutes to midnight. 2.5 minutes to midnight.
After Trump.
So I want to encourage.
No, seriously.
What concerns me about this is there's not much room to go.
Yeah. No.
So I mean, if you set it back, I want to encourage you to set it at noon. So let's say North Korea, launches an actual nuclear tipped missile that lands in Japan. Well, I would move it like an hour. You can only move it like 10 seconds.
Well, look, we talk about that every year, that there's not much real estate, and that enters into our discussion. And I think the point is, for me, and I must say I'm very honored to be chairman of the board of sponsors of the Bulletin of the Atomic Scientists, which was created by Einstein and Oppenheimer 70 years ago. And so and I remember when I was a student, I kind of revered the group, and so it's weird for me to be in it and in the position I have. But I view the derivative as more important than the absolute value. I mean, that's math terminology. But what I mean by that is, are events such that we move the clock forward or backward? Is the world getting more dangerous or less dangerous? Because the purpose of the clock is not to have some absolute significance. It's to alert the public of the dangers. First, the dangers of nuclear war, but now, since I've become chair, in fact, we moved it to be more the dangers of all emerging technologies, and now climate change is on our list, all existential dangers. The dangers now, for the very first time, the clock, when I announced it in Washington in January, cyber issues and their impact on democracy became a factor. And so what for one day a year, and I don't have the pretense that it lasts for much more than one day a year, every paper in the world covers this. And we raise in the public's awareness that these are real problems. People have become complacent about nuclear weapons because we haven't had a nuclear explosion against a civilian population in over 70 years. But these are real problems. And what we said, and what I specifically said in my statement and when we unveiled the clock, is that we cannot rely on our leaders to address these existential problems. We clearly can't. In general, we can't. But now it's obvious we can't. In issues of nuclear weapons, at the time, we moved it forward because of the statements. This was before Donald Trump was inaugurated. The statements he made about nuclear weapons, which are terrifying, and statements Putin made, and what was happening in North Korea. But also, to address climate change, we clearly can't rely on the world leaders. So what we said to the public is, you're the only ones who can change the world and make it a better place in the future. And the only way you can do it is care about the issues, and then impact on the political system. Because at least in democracies, or even pseudo-democracies, people want to get reelected. And the public can play a role. It's happened before. Happened in Vietnam. It's happened over and over again. And only if the public is not complacent about these problems do I see any hope that world leaders will address them.
Well, pseudo-democracy, I hope you're not referring to America.
I am.
I mean,
right
you
now.
you just witnessed democracy pushback this week. It works.
Well, I agree. Look, democracy. I'm not.
Okay.
But I do think we have to recognize there are extreme challenges to democracy that are happening right now. And I agree that I'm thrilled with what happened in some sense this week, but I'm also not naive enough to suspect that it's going to solve all our problems.
And also, by having...
But I was more excited by where democracy worked for me was more than when a bunch of old white men decided that they didn't want to punish women enough and they weren't going to vote for to take away the Affordable Care Act. For me, where I thought the first time I felt really positive was after the travel ban, when spontaneously the public showed up in airports around the country and said, no, we're not going to stand for this kind of. And I thought, and that's the first time I said, okay, look, that, and then in the same week when an appellate court decided the travel ban was unconstitutional, when the rule of law took hold, and when the public didn't accept the garbage, then I said, yeah, I have faith in that democracy is going to stand. For me, that was a much bigger moment.
You could not have done this in 1930s Germany. This is not a tyranny. This is not even comparable to that.
Well,
which is
I am
why
not so sure.
I'm also concerned about that clock being 3 minutes to...
There's the frog in boiling water, and we accept stuff today about Trump and about, that we shouldn't be.
I just worry that things... What do you mean he's accepting?
Well, I think things, become... we hear them so often every day repeated that people become complacent about that. They should be screaming.
I think they are.
Well, I hope you're right and I'm wrong. I really do. I just think I'm worried because I have studied recently what happened in the 1930s and for instance discovered that it was still a democracy even when Hitler took over.
Well, it was a democracy, but the press got squelched pretty quickly.
Well,
you could not do the kinds of things.
Well, that's what Sean Spicer's done to the press, and it's the first stages. When you keep out the New York Times from and the CNN from press briefings in the White House, that is not acceptable. And we should, that person should not be allowed to be press secretary. The administration that has that should be sanctioned. But instead we just say, isn't that amusing? Or I don't know what. But I don't think there yet been the consequences. Now you're right, it's an extreme, but it's a slippery slope, I think. And we have to at least watch out. And you're right that in this country the rule of law is still holding on many issues extremely well. And the public appears to have a limit of what they can take. But I do worry that limit might keep moving. But
and we're free to protest. And
I couldn't say what I do.
That's right.
And I couldn't. There's a lot of countries in the world where I couldn't say what I do.
That's right.
Or do what I do. But at the same time, and I know we disagree. It's great that we can find something to disagree about. There are unofficial ways to sanction people, to marginalize their protest. My good friend Noam Chomsky, who is my friend and maybe not yours.
I don't know him.
But I mean, what you may not agree with what he says, but I think he's presented many examples of how people who discuss such things as American foreign policy outside of a certain restricted range get marginalized. They don't appear on TV. They don't appear in the New York Times. They don't.
No, I see Chomsky all over the place, so he hasn't been marginalized.
Well, you do. You do. But I think he has been. As we pointed out, he wasn't in the New York Times. So he pointed out to me for 30 years. But I think there's an effective way, and I've seen it myself, that where if you are willing to state things in a certain way that just go beyond the pale, that you first of all.
I don't know. Bernie got pretty far as a.
Bernie got pretty far, but I don't think
marginalized person. He did pretty well.
Well, yeah, but he wasn't. I don't think he was anywhere near the range of what you would call left wing in this country versus what you could call left wing is still very small, in my opinion. Bernie would be nowhere near. Well, I grew up in Canada. Bernie would not be a left wing politician in Canada. Okay, he just wouldn't be. He'd be right in the mainstream. And in fact, in most Western industrial countries, he would be not even in the middle, I think. And so So it's amazing that we call Bernie left-wing, and he is in this country, but in most of the rest of the industrialized world, he wouldn't be. And so I think the United States, we tend to be a little too self-satisfied about what we allow, because you know, and I do, you read the press in other countries and you see ridicule for things that we accept in this country. And I'm not saying that they're better. I mean, I think one of the greatest things for me, of living in two countries. I grew up in Canada, I live in the United States, and I've lived in the United States longer than I've lived in Canada. In fact, I was born in the United States so I could be president. That'll never happen, but I could be. But unlike Ted Cruz. But anyway, but one of the greatest liberations of travel and living in another country is you realize this patriotism stuff is just garbage, at least for me. You know, it's an accident of birth. If I'd been born 300 miles further north, I'd be patriotic about a different country. And so I love many aspects of living in the United States. I hate many aspects of living in the United States. I love many aspects of living in Canada. There are things that drive me crazy about that. Every country has virtues, but to argue that somehow it's the best because of an accident of birth is something that, to me, I don't...
Sure.
And so for me,
yep.
I love the United States in many ways, and I noticed it when I moved from Canada. The openness on a personal level, the entrepreneurial aspect, which leads to so much chaos, is exciting, and there's much less of it in Canada in different ways. And so there's many things I like, but one of the things I realized right away is the spectrum of what you hear in the news is much more restricted in this country than many others.
All right, let's see, I want to continue. This is the lightning round.
Okay. Well, yeah. We have all night.
The thing on the clock. So here's what bothers me. So for 70 years, we've been just right on the edge of doomsday.
Well, it moved to 17 minutes once.
And it hasn't happened. So, you know, plenty of us say, come on.
Well,
you know,
look, it's an
what's the
arbitrary.
next
It's
thing
an
that's
arbitrary. It's an
No, I
arbitrary.
understand, but let me move on.
Okay.
Because now there's new threats. So again, lightning round. Give us your opinions. AI is the apocalypse. AI is going to
No,
bring
I don't think
doomsday.
anything is the apocalypse, but everything. We just had an event in my
But
origins.
that's okay. Give us your opinion on.
We just had an event on AI in my Origins project, and on the dangers. Well, the possible disruptive challenges. The future of AI. Who's in control? AI is going to change the future. And it's going to make the world a vastly different place than it is now. Now, there are scenarios you can imagine that will make it a seemingly horrible place. Some of those things that are horrible, by the way, may not be. Okay?
Like
it was
what?
pointed out, for example, in ancient Greece, people thought the development of writing was awful because it would
ruin
destroy
the
the
oral
oral
tradition,
tradition.
yeah.
Well, it did not turn out to be so bad. And you know, if AI is involved in ways that we now think humans should be involved in, it may lead to a better world. But AI could lead to many things. It could lead to the destruction of humanity. It really could. But for me,
How?
well, AI could decide, as one of the people who was on our meeting is Jan Tallinn, who developed Skype. And for example, oxygen is really bad for electronic systems. So you could imagine if AI eventually controlled things, they'd create a world in which the oxygen content in the atmosphere would continually decrease over time. And you can imagine it with life forms that, like we are, which would get in the way of electronic systems, would cease to exist. I think that's an extreme scenario. But what I think is really important is fortune favors the prepared mind. So burying your head into the sand and saying, I don't want to think about it, is bad. And also saying it's so miserable we shouldn't do it is ridiculous, because what's possible will be done in many ways. Instead, we need to foresee and look at the possible challenges and threats so we can anticipate them and decide how institutionally we might manage them or how to respond in advance to those things. So AI has a lot. Our meeting was amazing to me, and I learned a lot. I don't think it's the apocalypse, but it's going to produce a world, for example, which is constantly at war, but not physical war, which is constantly at war in the cyber world. It's already happening. We are constantly, every day, at war in ways we weren't before. And I don't see any hope for changing that.
This is the cybersecurity issues.
Yes, cybersecurity issues are already happening, and it's always going to be that way. There's always going to be defenses. And what's really good, by the way, is I realized, and it's something I learned in the meeting, is in most areas of war, offense always beats defense. Offense always is preferable to defense. Defense always costs more than offense. It's always less effective. It certainly is in nuclear weapons. The missile defense system is such a joke. I used to say when Bush announced in 2004 we're going to have a missiles defense system that's 93% fit, and or whatever it was, and it turned out most people in the United States, 50% of them anyway, thought we already had one. And I said, that's the way, great, let's just say we already have one, it's a lot cheaper, and it's just as effective. But in cybersecurity, defense is actually in many ways has a natural leg up, because worms can only access a certain amount of information, because then they make themselves visible if they don't. But the defensive systems can monitor the whole web and announce themselves, so they have much more access to information than the offensive system. So it's one area where defense may, it gives me hope defense may beat offense. But we're going to be in a world at war, and that's never going to change. But can we manage that and effectively, work with that and still have a manageable society? And I think the answer is probably yes. But so I don't think it's the apocalypse, but I do think it presents challenges, and we'd be foolish not to try and anticipate those challenges.
What about economically, taking people's jobs?
Well, I think there's two solutions. There's two futures I can see, and I'm, as my friend Cormac McCarthy says, I'm a pessimist, but that's no reason to be gloomy. I don't. So Keynes first talked about how industrialization will free us, right? Because sure, there won't be need for jobs for many people, so those people can be productive. They go to coffee shops, they can read books, and life can be better. And I do think that's one solution. The fact that AI is going to take a lot of jobs, and it will, could allow, if we had a sensible society, to share the economic benefits that come from AI. But we clearly live in a society that doesn't want to share economic benefits. We don't even want to share economic benefits when it comes to healthcare. We don't want people who do well don't want to pay for the health problems of people who don't. Now, if that's the world we live in the future, then what's clear to me is AI is going to produce mass unemployment and mass social disruption. So that's one possibility. But ultimately, we're going to have to confront that, and I think say, you know what? There are a lot of shitty jobs. Am I allowed to say that? Don't care. There's a lot of shitty jobs that AI is going to take over. And there are a lot of other jobs that aren't shitty. They're like doctors and maybe lawyers that AI will take over. Okay, but the society could maybe function better. And we can all economically function better. And the solution is to take the people whose jobs are removed and provide them the social welfare. Allow them the freedom to live better lives because of this.
You must be aware of the Star Trek economics, Trekonomics.
Yeah.
Post-scarcity economics.
Yeah.
I mean, essentially where we all have a replicator and you have everything you need for basics.
Well, there's talk about it in various countries. Scandinavia, giving people a guaranteed
basic income.
And I happen to think I'm all in favor of it. It has to be done right. When I grew up in Canada, there was a group in the Depression called Social Credit. I used to do Canadian history, and which said the solution to the depression is we'll just print money, but that wasn't the solution to the depression. But if it's done right, I think it's, But of course, in this country, it'll be labeled socialism or communism, and it'll be labeled, how dare we let these people who are lazy and indigent, we give them money because of the luck of something else we have money, and so I grew up in a country which by many standards, by American, is socialist, so I have no problem with that. But I think we're going to be confronted with the need to do it, and AI is going to be the way to do it. And what happens will depend on how we respond to that. And I am not optimistic.
Last question. Of the other potential threat, terrorism, Islamic terrorism, or whatever you want to call it. I know you're aware of the sensitivity of these issues.
Yeah, I get lambasted more and more.
But you've been an outspoken atheist and critic of religion, and yet we've seen pushback when you criticize, say, Islam. Not you personally, but if anyone criticizes Islam.
No, and I criticize people who are fixated on Islam.
Okay.
To me, I mean, Islam is. I said it on Al Jazeera. On Al-Qaeda.
That's what those helicopters were about, yeah.
I said it on Al Jazeera, and I was amazed they didn't edit it out. I said, Islam is no more stupid than the other world's religions. It isn't in a fundamental way if you read the Quran. It's no more stupid than the Bible. The difference is that people take it literally in a way that we did in the 12th century and 13th century.
Right.
And so, but in fundamental way, it's no more ridiculous. But
it's
I
the current
think,
ridiculous problem.
It is a problem. But I maintain, and here's when I've been much more vilified than criticizing Islam. I've been vilified for pointing out, and I really do think that the average American has so many more things to fear on a daily basis than Islamic terrorism,
of course,
that this
yes.
fixation
Yes, yes,
on Islamic terrorism is, to me, not only inappropriate, but for many people is a way. I mean, it's the 1984 version. You've always got to have an enemy that you
Right,
can
right.
allow to restrict freedoms.
Right.
And I am much more. I've just written a piece which I thought was going to appear in the New Yorker, and now it won't. And we'll see if I get censored by this unofficial censorship. I do think that the real fundamentalist threat in the United States is Christian fundamentalism. I'm much more afraid of that than the average American on a daily basis has much more to fear from Christian fundamentalism than it does from Islamic.
Now, you don't mean abortion bomber clinic.
No, I don't mean abortion bomber clinic. I mean like people like who want, like Mike Pence.
Yes, okay.
The people who want to close Planned Parenthood and reduce the health care for women, millions of people around the country. The people who want to take away education from our children. This is real, and it affects millions of people. It doesn't, it's true that terrorism happens and affects a handful of people, literally, in this country, far less than regular shootings on a daily basis. As I point out, I mean, any of the mass shootings, on a daily basis, there were 300 mass shootings in the United States last year, 325. They killed more than 4 people, and so but we fixate on the few that quote unquote are terrorists. But I think we have much more to fear from that kind of fundamentalism that restricts the rights and freedoms of people in this country right now, and does exactly what I think. The real people who suffer from Islamic fundamentalism are Muslims in Muslim countries. And why? Because the purpose of ISIS, of course they want to create terrorism, but the real thing they want to do is control the hearts and minds and lives of the people living in that country. And that's a threat to them. And what I believe is a bigger threat in this country is the people who want to control the hearts and minds and freedoms of people in this country. And we've got to work hard against that.
Doesn't sound like you're being censored.
Not here, but we'll see if that piece gets in any paper.
Well, it is our tradition from our wine
Yeah.
sponsor, Michael McCarran, and our company Etching, to have an etched bottle of your book cover. This is for
It's
you.
amazing. I'm very
Please
honored
thank
by this.
Lawrence Krauss.
Thank you. Let me just say one thing. I love doing this, and I love what you do, Michael. And I've done things with Skeptic for many years, and I've always viewed it as a privilege and an honor because it's just one of the things that makes us great.
All right.
Okay,
Well,
yeah,
good.
okay.